So this time I'll talk about transition-based parsing with neural networks. Did I mention party and everybody started partying? Okay, so I'll talk about transition-based parsing with neural nets, basically there's two kind of standard ways to express linguistic structure, syntactic structure anyway. So dependencies, as you covered, focused on the relationships between the words. And phrase structure looks something like this, where you have like phrasal spans and stuff like that. So I'm going to be talking about methods specifically in the context of dependency parsing here, but actually the transition-based parsing methods that I'm going to talk about can also be applied to phrase structure parsing. They can also be applied to semantic parsing. They can be applied to a lot of other things. So basically anything where you want to have a tree structure coming out of a neural network, transition-based parsing models are relatively easy to use, and they're the state of the art for a lot of tasks. So this is a good thing to know if you want to create any sort of tree structured output. All my examples will be from dependencies, just because it's easier to explain consistently, but I can also cover other ways to do transition-based parsing later if you like. So parsing, predicting linguistic structure from the input sentence, and transition-based models, they step through actions one by one until we have output as discussed. One thing to note here is specifically with reference to neural networks, these are like kind of history-based models for sequence-to-sequence models or part of speech tagging. So in other words, they're conditioning on all of our previous decisions, which is like what I talked about in last class, or the sequence-to-sequence models classes, for example. In contrast to this, there's graph-based models, and I'll be talking about these next class. And graph-based models are models that calculate the probability of each edge or constituent and perform some sort of dynamic programming. So the contrast this is like the CRF model for part of speech tagging. So when you look at these, think of the past two classes that I've talked about, one with the CRF models, one with the history-based models, and these are the connections between the two, I guess.
Question.
Yeah.
In the reading, it was mentioned that graph-based models can have non-projective arcs in the output, and transition-based models have only projective arcs. But the way you have distinguished these two doesn't seem to indicate that.
So did the reading say exactly that, or was it a little bit more nuanced? Because there definitely are ways that you can incorporate non-projective dependencies in transition-based models also. The standard, so the standard way of doing dependency parsing, like arc standard or arc eager, cannot handle projective. It can only handle projective ones, but graph-based models in general can do non-projective ones. I don't remember that exactly from the reading, so I'll have to go back and look. But that's the actual distinction, I guess. Any other questions? It's definitely, yeah, so it's definitely easier to do non-projective in graph-based. So in shift-reduced dependency parsing models, transition-based shift-reduced models, so one question is, why would you want to use dependencies? This is something that you should think about also, not when you're just using, not when you're just thinking about parsing, but also if you're thinking about using any sort of tree structure in your model itself, even if it's not a parsing model. Dependencies are often good for semantic tasks, for example, question answering or other things like this, because the relationships between words that affect each other are very directly expressed. So you can also create labeled dependencies where, for example, you say this is a preposition, this is an object, etc. And you can also use these in models if you so choose. So Just to give a little bit of contrast, if you have a phrase structure model, to go from saw to with, or saw to girl, you need to go up the tree to the verb phrase, to the noun, and get girl. So to basically find out what was seen, you need to travel much farther through the tree for phrase structure. On the other hand, I'll get there in a second. On the other hand, phrase structure is often good for things like translation, where you want to keep phrases consistent or whatever. So they have different uses for different things. So was there a question?
When you said good for semantic tasks, like you gave a couple of examples where adding this has shown to help a lot.
So some examples where these have been shown effective are stuff like question answering. And the reason why is because one of the things you want to know in question answering is who did what to whom. And if you look at dependencies, it's a single arc away, so you can directly model those. But if otherwise, you're many words away, so it becomes more difficult. That being said, in neural networks, if you have LSTMs, the gains are much less large, but well-engineered models tend to be bigger. Another one is sentiment analysis. Dependencies, tree LSTMs over dependencies were shown to do better than others. So, yeah.
Why do I need directed edges? Can I just live with undirected edges?
That's a good question. So couldn't we live with just undirected edges? And the answer is probably that wouldn't be a good idea. And the reason why is because the head of a dependency and the child of a dependency have very different, functions, I guess. So the head of a direct object dependency is a verb, and the child is a noun.
If you construct a tree, then you're essentially ignoring head and
Well, the directed edges, the edges always go from the head to the child, so that's why directed is important. Any other questions? No? Okay, I'll proceed then. So arc standard shift reduce parsing, like was covered. We have process words one by one, left to right, two data structures, a queue or a buffer of words in a stack of partially processed words. And at each point choose, you can move one from the queue to the stack, or reduce left, reduce right. So this was in the reading. And the important thing here is if you choose the right actions all the way through the sentence, then you get the correct tree. If you choose the wrong action at any point, you'll usually get an incorrect tree. So yeah, we have an example. We shift to move from the buffer to the stack. Shift. Wait. That should actually be reduced. Sorry, that's a bug in my slides there. So we reduce left. I think I have an off by one error in my slides. Sorry. So yeah, that's reduce left and then shift. And then shift, reduce left, reduce right, and then reduce right, and you're done with the thing. So yeah, sorry about that. I'll have to go back and fix the slides. So anyway, yeah, this is how you get the structure. And classification, given a configuration, including your stack and your queue or your stack and your buffer, you have something like this, and then you choose which action, shift, left, or right. And based on the action, you'll get a different tree, and obviously you want to pick the correct one, not the incorrect one. So making classification decisions, you extract features from the configuration, what words are on the stack and the buffer. For example, what are their part of speech tags, what are their children. And one really salient thing here is feature combinations are important to solving this. So for example, if the second word on the stack is a verb and the first is a noun, then there's a very high chance that you'll want to draw an edge from verb to noun, right? Because nouns tend to be children of verbs. So this and is important, and if you remember, neural networks are really good at combining together features, so they can learn these combination features very effectively, which is why neural networks are a good are a good fit for this. These combination features, you used to create them manually. So you used to go and say, create a whole bunch of feature templates that say, oh, I think these combinations of these two features are really important. These combinations of these three features are really important. Now we use neural networks to learn these feature combinations. And for the rest of the class, this was all review kind of up until this point, and now I'm going to talk about the neural network part.
How do you tell the neural network what words are on the stack or the buffer? Like what kind of representation?
Yeah, I'll talk about concrete methods to do that in a second. So this was all general stuff about neural networks, and then the first one about this was by Danqi Chen at Stanford, doing a feed-forward neural model for shift-reduce parsing. And basically, the idea here is up until now, we knew that part of speech tags were important. We knew that words were important. We also knew arc labels were important. But we didn't know exactly which combination of all of these was important. So the kind of straightforward thing to do here is basically to say, okay, we are going to embed all of our words. We're going to embed all of our part of speech tags, and we're going to embed all of our arc labels. And specifically, so I'll explain in the next slide, like what exactly which words we're talking about, exactly which part of speech tags we're talking about, which arc labels. But basically, the idea is you create this big vector, and then you have this this hidden layer with something called the cube, a cube activation function, where you basically do a matrix multiply over parameters and all of these inputs and get a hidden layer. Take the cube of that and then use a softmax to predict your remaining mentions. So notably, this has no recurrent neural networks. It's just a feed-forward network that's learning to do feature combinations better than our previous methods that were able to do them.
What do you mean by cube? Like a cube?
Like literally the cube, the element-wise cube. And I'll explain why in a second, but it's kind of this was very unusual, and I haven't really seen anybody using this since then, but it worked very well for them, and there's a reason for that. So then the question is, what features do we want to put in our big feature vector that we use to make our classification decisions? So what they did was they chose the top 3 words on the stack and the buffer. So you look at the words on the stack, you look at the words that you haven't processed yet, you take their word embeddings. The 2 leftmost and rightmost children of the top 2 words on the stack. If we go back here, he is basically the leftmost child of has. So you add that also to your feature vectors. And the leftmost and rightmost grandchildren, and part of speech tags of all of these words. So the arc labels of all the children and the grandchildren. So this is an additional 12 features. So basically, you're extracting. When I say features, it's actually kind of feature embeddings. But you extract all of these and run them through the feed-forward network that I talked about before. As their nonlinear function, they used a cube function. So basically, you take the cube of the value that you calculated according to this. Normally, we take a tan h or something like that, right? So normally, our nonlinearity is a tan h. Instead of that, they decided to use the cube. So why do you do this? The reason why is basically because it directly extracts feature combinations of up to 3, essentially. So up until before neural networks, what people would do is they would use support vector machines with a polynomial kernel. So if you're familiar with support vector machines and kernels, basically they calculate these feature combinations according to like the cube of all the features that you input into them, or something similar to that. And the idea here was to do a similar thing in neural networks. Now, the advantage of neural networks over kernels is that basically kernels, you have to remember your entire input data. So if your input data gets very large, they get very slow at test time. So this is an attempt to do a similar thing, except with neural nets, which don't have that problem. So if you look, basically, this cube activation function can extract these kind of three combinations of three features, essentially. And the result of this was basically that it's faster than most standard dependency parsers, doing 1,000 words a second. And they also used a pre-computation trick to cache matrix multiplies of common words that made this very fast. And it had strong results. I have an example of this. If you want to take a look at what a feed-forward dependency parser looks like. But I'm not going to actually walk through the code because it basically implements these equations as is. So that is a brief summary of what they did. Yeah.
If the cubic features were actually important, shouldn't the intermediate layers sort of have learned it on their own?
So they compared to basically the cubic function is the intermediate, is the activation function for the intermediate layer, and they compared it to other things like the tangent tan-h function. And they found that this one worked better. And I guess the reason why it works better is basically it's easier to learn these combinations of three features in a more direct way than it would be to do in the other direction. So as I said, you can do a similar thing with a regular tan-h. You can do it with any nonlinearity, really, but this was the one that they chose for here. So one comment about this is one of the big selling points of neural networks is you don't have to do feature extraction, right? The neural network will extract all the features for you, and all you have to do is train an LSTM, and it will do dependency parsing for you or something like this. But if you look at this work here, actually, we have a huge number of feature templates, right? And these are all hand-engineered based on our previous experience on dependency parsing. One advantage of this is by doing this, they can make this parser super fast. It's still one of the fastest parsers that people already use. But of course, people still use. But of course, this is not ideal. We don't want to have to continue doing this if we can avoid it for every problem. So let's say we wanted to not do dependency parsing, but some other generation of tree structure. We'd have to rethink about all of our assumptions that went into designing this model. So before I talk about a better way to do this, I'm going to do an aside. So this now has nothing to do with parsing. This has to do with using tree structures in neural networks for anything. This could be for classification, it could be for translation, it could be for dialogue or anything. So assuming we have a tree structure that we would like to use, we can use it in this way. So why tree structure? I kind of talked about this already. But one reason why is because tree structures are very natural ways to model things in a simple way. And when I say simple, I mean on top of a tree structure, you could almost write rules that allow you to solve some of these problems. So, for example, for sentiment analysis, you have one kind of tree structure specifying a phrase on the left side, and this phrase is very negative. And then you have another tree structure on the right side, and this structure is relatively positive about a movie. And then you get up to the very top of the tree and say, okay, I have a negative thing on the left side, and I have a positive thing on the right side. What should I do? If you know English, what would be your intuition there? Positive, yeah. So generally, there's lots of cases where you say something at the beginning of the sentence and then you say but, or you say something else and you contradict the thing that you said at the very beginning of the sentence. So in order to be able to say this, you need to know what the salient concept in language is. You need to divide it into two, basically into two phrases and then combine them in the appropriate way. And tree structures are a very natural way to do this in every language in the world, because every language in the world is recursive in its structure. It builds up larger phrases from smaller phrases. So that's, I guess, the motivation here. And this is true for any task that you can think of. Yeah?
So there's many ways to create this tree structure, right?
Mm-hmm.
For the kind of thing that you mentioned, is a phrase-based structure better or a dependency arc type of tree better? Which will separate these two things?
I think you can have intuitions about that, but in the end, it's kind of an empirical question. So, like your intuition, I guess your intuition about that is if you think phrases are important, if you think properties of phrases are important, phrase structure is probably better. If you think the interactions between words and like who did what to whom is more important, then probably dependencies are better.
Probably just try them both.
And if you can try them both, that's the easiest thing to do. Once you've created a tree structured neural network, it's not too hard to run a dependency parser and a phrase structure parser. So you can certainly try both, but yeah, I'd say that's my suggestion. So I'll start out with recursive neural networks. So the idea, we have recurrent neural networks and we have recursive neural networks, which is very confusing. I prefer to call these tree-structured neural networks just to make it very clear what the difference between a recurrent neural network and a recursive neural network is. But basically, the idea of a recursive neural network is it's a generalization of a recurrent neural network where you can have more than one node going in to generate a new node. So what it would look like is we have a predefined tree structure for this sentence. Let's say we have a phrase structure parse of this sentence. So this movie is a phrase, so we combine these together in a tree structured neural network. Hate this movie is also a phrase, so we combine them together according to this. And I hate this movie is a phrase. So then at the very top, we combine these together. And for all of these, the tree RNN is the same function. It has the same, probably has the same parameters for all of these. And it just takes in 2 children and generates 1 node for this child. And if it's a binary tree, then it's relatively simple to do this all the way up to the top until you have 1 vector for the entire tree. As a result, you also get 1 vector for every phrase in the tree, if you'd like 1 vector for every phrase in the tree as well. The simplest version of this is just this. It's a thing where you concatenate the representations of the two children and multiply them by a weight matrix and then add a bias vector and take a tan each, and then you get your new representation. Yeah?
When you say representations, do you mean the embedding representations or do you call them on like parsing? Do you pass it through a regular network?
Well, when I say representation, I mean a vector, basically. It's a vector representing that particular, part of the tree. So the red ones would be probably looked up for each particular word, and then the purple ones are a result of composition. Usually we kind of assume that these are in the same space, although you could probably relax that assumption if you wanted to. Yeah?
So how do you actually construct the tree? Is it always specific structure or?
So in this case, I'll talk about that a little bit later, but in this case, in the case of recursive neural networks, usually the tree is given. You assume the tree is given, and then you just want to compose along that tree. So actually, I realize this slide is a little bit hard to interpret, but you would assume that you already have a syntactic parse where I'll not write everything there, but we have something that looks like that, and that's given, and then we compose it along that. Any other questions? No? Okay. So this is one way to do things, but this actually doesn't work that well at all. So why doesn't this work? Why doesn't this work very well? Any ideas? Sparsity. That's not the main reason why. So, as an auxiliary question, this is very much like a regular recurrent neural network. So if we remove this extra thing here, this would be like a regular recurrent neural network. Does that give a hint about why this doesn't work very well? I heard two things. What? Because of the depth. Yeah, because of the depth of the tree. So as this tree gets deeper and deeper, you're doing more and more steps of a regular RNN. And as we discussed during the regular RNN class, RNNs suffer from gradient, disappearing, vanishing gradients. So our solution for that, for the regular RNN, was LSTMs, basically, or something like gated recurrent units. So there's a solution to this called the tree structured LSTM, which is an LSTM for tree structure. Go ahead.
Sorry, jumping back, I might be misunderstanding something, but I kind of fail to see why the tree RNN structure is different from just a feed-forward neural network that you're stacking.
Oh, okay, sure. So actually, from this example, this looks a lot like a feed-forward neural network. It would be different if we had a more complicated tree, like the dog chased the cat. And in this case, we have a tree structure like this. And if we had a recurrent neural network and I wanted to draw it kind of like a tree, the recurrent neural network would first have maybe the, and you would compose the with the previous state, which is null, essentially. And then you would add dog, you'd add chased, you'd add the, and you'd add cat. So basically, a regular recurrent neural network is like a, this is upside down, so that's hard. It's like a left branching tree, I guess. This is not a left branching tree. It's a tree that branches in the appropriate places based on the linguistic structure of the sentence. So it will be composing in a different order than a regular recurrent. Yeah.
Is there an effect wherein, like in this example, the vector of I will dominate the vector of movie because it is coming up later in the later stage?
Yeah, that's very reasonable. That's also a problem that's kind of fixed in the tree LSTM as well. Oh, sorry. In case you didn't hear, the point was I comes much later in the tree than movie. So wouldn't I kind of dominate your representation? You could also argue that that's a problem for regular recurrent neural networks or LSTMs as well. So I agree that things with less depth are going to dominate more. On the other hand, for things like dependency trees, the head of the sentence is the thing that's closest to the root of the tree. So in that case, actually the head of the sentence is the most important word in the sentence usually. So if that's the case, then that might be a feature, not a bug, I guess. And yeah.
Do the nodes of the tree RNN have to be the same thing, or can you leverage tags based on like the examples?
Do the nodes of the tree have to be the same, or can you leverage the tags of the tree? Yeah, so actually, I skipped over that and was planning on going back to it, but since you mentioned it, you can also parameterize this W by the tag of the tree. So like, I want to compose differently for noun phrases or verb phrases, etc. So that's the most common way. You could also probably treat the vectors differently, but I think it's more common to treat the parameter vector. Yeah.
So for that, would you need a software inside of the local image?
So in this particular case, right now, we're assuming that we know the label. Like the entire tree structure, the label was given to us. So we don't need to predict the label in this case. In later cases, I'll talk about how we use this in parsing, and then we would need to do that. Any other questions? Okay. So next is the tree structure to LSTM. As I mentioned, this is a method that basically applies the idea of LSTM directly to tree structures. And there's two varieties proposed in this paper. One is the child sum tree LSTM. And basically the idea is the parameters are shared between all of the children. And you could also, do grammatical label if you had a dependency tree with labels. But basically the parameters are shared between all of the children. And the LSTM forget gate value is different for each child. So basically what this looks like is, let's say we have the example of I saw a girl with a telescope. And at the very top, we have we have three children for SAW. So basically, to get the representation of SAW, we'll be wanting to combine together these three children. And when we do so, basically we run the same LSTM update. We run an LSTM update over the vector representation of the child. So each of these have their vector. And then we call the same LSTM function with the same parameters over all of these. And the only thing that varies between them is the forget gate. So the forget gate, if you'll remember, basically tells you how much do you delete the information in these vectors. So by doing so, now we have a separate forget gate for this one. We have a separate forget gate for this one, and a separate forget gate for this one. And so what we could do is we run the same update for all of these, but then we might use only the first section of the left child, the middle section of the middle child, and the last section of the right child, by choosing to forget all of the other information for irrelevant information for each one. So there, let's say we had the intuition that the thing on the right would be more important. Then for the thing on the right, we would basically forget less, and for the thing on the left, we would forget more. Yeah.
The number of children has to be fixed, right? Otherwise you can't.
So not for the child someone.
Not for child someone, but if you ignore individual children.
Right. So yeah, actually, as I was saying that, I realized the left and right example is not very good. So let's say you wanted to forget. Or you had a composition between adjectives and nouns or something like that. And you know nouns are more important than adjectives when you compose the two together. That way you can basically look at this vector here and say, does this look like an adjective or does this look like a noun? And if that's the case, I'm going to turn on the forget gate more for the adjective than for the noun. The next one, let me explain the next one and I'll explain the difference between them. So the next one is the n-ary tree LSTM. And basically for this one, you have different parameters for each child up to n. So in this case, if you have binary branching trees, I guess dependencies are a little bit harder to express this way. But let's say we had a binary branching tree where we had girl and this. Then for the first child, we would have LSTM1. And then for the second child, we would have LSTM2. And then if we had a third child, we would have LSTM3. For a fourth child, we'd have LSTM4 up to n. And then for all the remaining ones after that, then you would just use LSTMn, for example. So the difference is, for this one, all the parameters are shared among all the children, so you can have an infinite number of children if you really want, and all of them will be treated equally. Whereas for the n-ary tree LSTM, the first, second, and third, and et cetera.
It's having different LSTMs, if I just concatenated the embedding with like a one-hot representation of which child this embedding is coming from, you think it would work just as well? Because I don't need so many different parameters now. It would just forget based on that.
That's a pretty good idea. As far as I know, they didn't try that in that paper. So if you just concatenated an embedding of which child it was. Yeah, that sounds interesting. I feel that maybe somebody has done that at some point.
Or maybe they did and it didn't work. So.
Yeah, quite possibly. Was there a question over here? Yeah.
Doesn't this become incredibly dependent on like the ordering of children?
Doesn't this become incredibly dependent on the ordering of children? For this one, yes, it does. And then you could think that for a language like English, where the word order is actually really important, this is a good choice. And then for another language where the word order is less important, you might prefer the first one. So I don't know, Latin. Although I don't know. I don't know if you want to do NLP on Latin, but if you do, then that might be a good choice. Any other questions? Yeah.
Does the second method suffer from the data sparsity?
Does the second method suffer from data sparsity? Yes, I guess it does. Especially if n becomes very large. I think it's most common to use this on binary trees. So you binarize the tree and then use this on top of that. And if that's the case, then it's just 2. So, anything else? Okay. So another method that people have used, this came out about the same time as the tree LSTM. And the idea is basically that you just have a single bidirectional LSTM on top of the vectors. So the way it looks is you have these vectors, and then you have a separate LSTM where you just feed these in the forward direction, and then you feed these in the backward direction. And then you take the very last one from the forward LSTM, the very last one from the backward LSTM, and create new vectors. So this is just another way to do it. This requires less engineering than a tree LSTM by a slight amount, but it's just an alternative way. The good thing about this is it's very natural to capture the ordering of the words, and you can just learn things arbitrarily according to that. But both have seen wide use, I guess. So if you want to take a look at the code, we have example code for this as well. And it's actually really simple. I think it's like 15 lines of code to implement the tree LSTM. So it's not difficult at all. Yeah, so that was, yeah.
Can you batch operator for any of this?
Can you do batch processing for this? The answer is yes, but it's not trivial. There's basically 2 ways. One way is if you come up with a specific model, there's a way you can express the tree itself as a sequence of shift-reduce actions. And by choosing the shift-reduce actions in your composition function judiciously, you can essentially batch together things that are of the same length. The much easier way to do it is we have a method for automatically batching things together. So what you do is you just run over all your sentences, and it automatically batches the computation together for you. So one thing that you should know about this is it's way harder to batch than most other things that you can do if you don't use automatic batching. But if you use automatic batching, it's actually very easy. Yeah.
What were the gains? Were they significant? Like the tree LSTM and just normal LSTM, or even the
yeah, the gains for this are significant for the task that they tested it on at the time. There was actually a very nice follow-up paper, which I think is in the reading material, but maybe not, that examines for which tasks, like they make a strong tree-based baseline and they make a strong sequence-based baseline, and they compare the two. And the answer for that was sometimes it really helps. Sometimes a sequence-based method is just as good. The ones where it really helps are for tasks where syntax is very relevant, like semantic role labeling, for example. There's a very strong connection between syntax and semantic roles. I don't know if that's in the reading material. If it's not, I'd be happy to post it on Piazza if somebody reminds me after class. Okay.
If it's really important for something like semantic role labeling,
Mm-hmm.
and if I don't use a tree structured thing,
Uh-huh.
and I just use a normal LSTM,
Mhm.
and if I have like some kind of like a pairwise attention layer in between, do you think the tree could be induced? Like if it's that important?
If you have sufficient labeled data for semantic role labeling, which is usually not the case. But that being said, a lot of these comparisons happen before stuff like self-attention, and self-attention is an interesting thing that could potentially pick up things that look like tree structure. That being said, tree-structured LSTMs or whatever tend to work better than convolution, which is also similar in nature. So I don't know the answer to it, but it'd be interesting to know the answer. Yeah, another auxiliary thing is this kind of stuff tends to work really well for tasks where data is limited. So if data is not limited, making an extremely big convolutional neural network or an extremely big LSTM tends to work pretty well. This might work a little bit better, but when you don't have very much data for your task, this can really help like a huge amount. Okay. So now I will talk a little bit about parsing again. So there we go. And so now we'll talk a little bit about a method for parsing that basically incorporates this tree structure in a very natural way. So hang on one second. So basically the idea here is, if you remember back to the parsing that I was talking about, the difficulty there is encoding your parsing configuration in a good way, basically, in a way that's linguistically appropriate and captures all the stuff that you want to, know. And before that, they made a bunch of feature templates to try to capture this information, but feature engineering is hard, and we would like to avoid it if we can. So the idea here is, can we encode all the information about the parse configuration in a good, motivated, efficient way using something like a recurrent neural network? And the information that we have is the stack and the buffer and the past actions that we've taken. So the answer to this is basically, one answer to this, not the only one, is a structure that basically, in a relatively straightforward way, encodes the stack and the action space and the buffer. So the buffer basically is all the words that we haven't parsed yet. And so if we have an over hasty decision was made as our sentence, and we're currently on our buffer, we have was made. Then we basically have a backwards LSTM that goes from the end of the sentence to was. And this encodes all the information left on the buffer, basically. Another simple thing we have is a LSTM over the previous actions that we've made, which are our shift or reduce actions. So these take in the embedding of the actions that we've taken. So these are both straightforward. These are just LSTMs over sequences of things. Then the most interesting part of this here is how we encode the stack. So what the stack is it's basically words or also subtrees of the dependency tree. And we have an LSTM over the words or the subtrees of the dependency, representations of the subtrees of the dependency tree. So we can embed words, and the important thing is now I've talked about syntactic composition functions, right? Tree structured composition functions. So actually we already know how to embed trees. We use the tree LSTM, we use a by LSTM over the children, etc. So based on that, if you think about it, this S LSTM over here, this is just also a sequence LSTM, but before we put the stuff into the sequence LSTM, we encode the tree using something like a tree LSTM or a composition function. So the good thing about this is now we have all the information about all the things in the sentence. We even have all the information about all the trees that we've already parsed. And if you remember in the manually designed feature functions that we had for each of the, for the previous one, we had things like what is the left child of the current thing on the stack. And so by having a tree structured composition function, we encode this in the vector that we feed in to the LSTM encoding our stack. We can embed words, we can embed tree fragments using syntactic composition. And now the contents of the buffer are just a sequence of embedded words. So periodically we shift from this sequence. And the contents of the stack are also a sequence of embedded trees. And we periodically pop from this and push from this. So basically we have our standard computer science or data structures 101 data structures that we need to handle in an appropriate way, either a queue or a stack. Sequences, of course, we can use in RNN. What we could do is we could just run an RNN for each state. So every time we get a state, we could run an RNN over it again. But this would be a waste of time and memory. So this method uses something called stack recurrent neural networks. And basically the idea is you augment the RNN with a stack pointer, which has 3 constant time operations. Basically you push, so you read input and add it to the top of the stack. Or you pop, you move the stack pointer back to your previous input, or you embed. So basically this returns the RNN state at the location of the stack pointer, which summarizes the current contents. So an example of this, you start out with the initial state. You basically run the RNN forward for one step. Then you can pop back to the previous state. Then you can run the RNN forward again to calculate the next thing over here. You could pop once more and do this. So basically, by doing this, what this means is you don't have to recompute this y0 every time. And you can do this efficiently in basically constant space over the entire sequence. So we have an example of this too, how you implement this in this code sequence here. So yeah, I actually forgot to put the results for this method up here, but the results for this method are quite a bit better than the kind of simple approaches that you could think of. One being the previous one that I explained using just feed-forward neural networks. Another one being one where you treat parsing as a sequence-to-sequence model, and you output basically a tree of bracket. You output a sequence of brackets and try to call that a parse. So this method works quite well, or worked. It was definitely state of the art at the time, and it's still pretty competitive with the state of the art. Another method that basically uses this as a generative model of language is still probably state of the art for phrase structured parsing. Are there any questions about this? So up until now, I've talked about shift reduce is a method for dependency parsing, but what I want to emphasize is this can be used for lots and lots of other things. One of them is phrase structure parsing. Basically, if you want to generate a phrase structure, if you want to generate a tree, you can create a shift reduce algorithm to generate it. There's a bunch of methods to do this. These go all the way back to before neural networks, but just to give a very brief idea. So you have methods, you have actions that are basically shift, reduce x, or unary x, where x is a label. So if you have a tree that looks like this, you first binarize the tree, so you get a tree where all of the branches are binary. So if you remember CKY or Chomsky normal form, this is a common thing that you do. And then you have actions where basically a shift moves something from the buffer to the stack. Reduce NP prime would take the top two things on the stack and put a phrase structure label NP prime over it. And then you can do things like unary S, which basically adds a unary connection between the top of the stack and the next leg, or sorry, the next and the subtree. So I think this general sketch, from this general sketch, you can see that by combining together these actions, also you can create these trees. Are there any questions about this? No? Okay. So what follows up after this is actually the generative model that I talked about. So this is a model that basically generates phrase structures and sentences at the same time. So you can think of it basically, our problem of parsing is if you take in a sentence X, you want to generate a tree Y. In this case, we're creating a generative model where we generate both the tree and the sentence at the same time. So why would we want to have a generative model? There's, I guess, maybe 3 reasons. One reason is that you could use this for something like, something like a language model, which is what they actually evaluate in this work here. So basically, what you do is if you marginalize over trees, if you sum over all the possible trees, you can calculate the probability of your text. And what language models do is they calculate the probability of text. So this is a language model. Of course, you can't sum over all the possible trees, but they have some tricks in the paper that allow you to do this. Another reason why you might want to do this is because you could use it as the output side of a generative model. So let's say instead of a sequence-to-sequence model, you wanted a sequence-to-tree model, you could use a generative model of text to do that as well. So this has a transition sequence. And the transition sequence, basically you have a stack, and you have terminals. And the difference between this and a shift-reduce parser is, remember, the shift-reduce parser has a buffer that's already available to you. So in this case, because it's a generative model, we need to generate sentences from left to right. So we can't look at the words that we can't look at the words that we're going to generate in choosing our next action. So the idea here is we need to basically condition all of our actions on just the past things that we've done. So it has a transition. It basically has a transition sequence which is non-terminal. So you then generate the words. Generate the non-terminal labels, and then when you, instead of shifting, you generate a word, and you need to choose which word you're generating. Yeah, this can serve as a language model as well. This has good parsing results. So basically, this is the model that I mentioned. It is one of the kind of state-of-the-art models on phrase structure parsing. And another thing, but one thing to be aware of here is it's very difficult, given a sentence X, to generate a tree Y. And the reason why is because if you want to search for the trees, basically at the very beginning you're searching entirely blind. You don't have any information about the terminals when you generate S and then NP. And because of this, you have all the possibilities for your first couple non-terminals. So you basically have a lot of trouble generating the first part of the tree. So it's difficult to search. So what they do instead is they generate with a discriminative model first, so the stack LSTM model, and then they re-rank the sentences with this model. So yeah. So this is an interesting paper that you can read. There's a lot of technical details in there that can also be useful for other things as well. Are there any questions? No? Okay. So finally, there's a very rough approximation of a tree structured generation model. So this very rough approximation of a tree structured generation model is it's similar to the RNNG model, but instead of using a model that does any sort of syntactic composition or things like this, it just generates symbols of a linearized tree. So what this looks like is you take the tree, the parse tree, and you turn it into a sequence of brackets that are annotated with their phrase, essentially. And by doing this, then you can run just a normal sequence-to-sequence model over this and generate a tree. This has a huge advantage in that it's super easy to do. You just need to write a pre-processing, then you can take your normal, awesome neural machine translation system and then just translate from English to trees. The downside to this is it has no explicit composition function like a stack LSTM or RNNG, and it's also not guaranteed to output well-formed trees. I think in the original paper they say this failed 5 times on our test set, so we just added brackets to the end of the trees until we got a well-formed tree. So you're not guaranteed to get something well-formed out of this. And also empirically, the ones with explicit composition functions are a lot better. But that being said, ease of implementation is a very strong, recommending factor for some things. So if you don't really care if it's really good or not, you want something that's pretty good, then this is something that you could also consider. So that's all for my my presentation today. Are there any final questions? Yeah.
We spoke about tree LSTMs and stuff.
Yeah.
I think of late there's a lot of work on neural networks for graphs as well. Do they have any applications in NLP?
Neural networks for graphs. Yeah, I'm going to talk about that in 2 lectures, I think, if I remember correctly. Yeah. I won't talk about them now because I will talk about them. Anything else? Okay. Thanks a lot.